I welcome you all in this course of Introduction to Heat Transfer, a practical oriented approach. Today is lecture number 2, Thermodynamics versus Heat Transfer. So in this series of lecture, you will have 14 lecture, and as I said earlier, you will have assignment on each lecture, and that assignment will be provided through the online mode. The online link will be available in the description box. Also, the lecture notes and the ebook for this entire course will be available in the description box. So you will have an open discussion, and I must say that feel free to contact me with any doubts in this course. So today is a lecture number 2, Thermodynamics versus Heat Transfer. So basically in this lecture we are going to see that how the thermodynamics and the heat transfer in different ways, how they plays an important role in our engineering and in the applications of the engineering. So how they differ with respect to their properties. So we are going to see that. So let's start. Okay. I am Amraraj Sawant, Assistant Professor from the Department of Mechanical Engineering. Okay, so let's start. Conduction to energy. So energy exists in many forms. Okay, basically the thermal energy, mechanical energy, kinetic, potential, electrical energy, etc. So these kind of energy are all together form the total energy of a system. Okay. The system is a controlled mass or controlled volume system, or maybe controlled pressure system. Okay, so the total energy is a sum of these all forms. Likewise, I said the thermal energy plus mechanical energy plus kinetic plus potential plus electrical and etc. All these add together will form total energy of that system. Okay, so internal energy, the internal energy of any system. Okay, the internal energy of any system is a microscopic energy within that system. Okay, a microscopic energy due to their particle, due to the motion of their particle, or due to the motion of their atoms or molecules, whatever the energy formed in a molecular level inside the system is called internal energy. Okay, and this internal energy plays an central role in thermodynamics. Okay, so basically what is meant by thermodynamics and what is the relevance of internal energy in the thermodynamics? So study of energy, heat, work and the system properties is better way known as a thermodynamics. Okay, so in thermodynamics we are focusing these concepts all together at equilibrium states. At equilibrium states means what? At the start point or at the end point of any process. Let's say we are hitting a rod. In previous lecture I have given an example of hitting rod from one side to another side. Okay, so for that rod, if the starting phase or starting point is just the hitting and end point is just a cooling, then the end states are important in thermodynamics. Okay, so that's why we are focusing that these starting and end point of any state is to be equilibrium, is to be maintained. Okay, at equilibrium state. So key concept is energy transfer in thermodynamics. So energy transfer from starting point of any process, let's say heating, to the end process of the heating, that to be in equilibrium states, equilibrium is important in thermodynamics. Okay, so real life relevance of this thermodynamics plays an important role in engineering, like as in IC engine, like is in refrigeration and power cycle. Power cycles which are used or which are generally used in a power plant to deliver power output in the sense of electricity and in mechanical terms. Okay, so basically the thermodynamics is a branch that correlates or that studies the end state with the equilibrium states. The end states or starting state or starting point or end point must be in equilibrium, and to study the heat, work and that properties of that system, the energy, work and system and that system properties is termed as thermodynamics. So what plays an important role of internal energy in thermodynamics is that the internal energy of any system at a starting point of any process or at the end point of a process to be in equilibrium, that is to be calculated and analyzed in the thermodynamics. Okay, so next, laws of thermodynamics. To understand this thermodynamics, that is the equilibrium states we are considering and the analysis of that equilibrium states. Equilibrium states means the properties are to be at a constant with respect to their positions or with respect to their time. Okay, so for understanding the thermodynamics, basically we have to understand the basic laws behind that thermodynamics. So zeroth law. So let's say in this figure, sphere A and sphere B are in thermal equilibrium with each other. Okay, so in same figure, the sphere A and sphere C also are in thermal equilibrium with each other. Then it is according to the zeroth law, the sphere B and the sphere C are also in a thermal equilibrium because A and B and A and C are in thermal equilibrium. That's why we can assume or we can predict the temperature or thermal properties with respect to A, B and AC of B and C. According to the zeroth law, if the two things are each in a thermal balance with the third thing, then they are in a balance with each other. Okay, and it is used for measurement of temperature. Okay, so first law. So first law tells us about if any in a system, if I put Q, that is means if I provide a heat in any system and that system is going to be deliver some work W, then the change in internal energy because of this means if any here this circle is forms a system. Okay, so if I put a heat, okay, if I put a heat in this system and this system is going to be deliver some work, then what is the change in internal energy of that system is provided from this first law of thermodynamics. Okay, that is energy conservation. Okay, what is mean by energy conservation? As per the statement, you have known that the energy can't be created. Energy just is nothing but change from one form to the another form. Okay, so in here by seeing this figure, if I put Q, that is heat, in this system, that is energy, okay, and some work is going to be delivered, that means some energy is also going to be delivered, then what is the change in internal energy? That is nothing but the heat minus the work done. Okay, and that is why the first law of thermodynamics tells us about energy conservation. That means energy can't be created nor be destroyed, it is just a conversion from one form of the energy to the another form. Okay, so here heat is converted to work, or in another system the work is going to be converted to heat. Okay, second law of thermodynamics, in before I think so in the first lecture, okay, I have just stated this second law of thermodynamics, like as a heat is always flow from hot end to the cold end. That means at a higher heat is always flowing from higher energy level to the lower energy level. Okay, so this form of or this conversion of heat from higher energy level to the lower energy level might be having some dissipation or some leakages. Okay, and that leakages is nothing but entropy or disorder in the form of the energy. The heat which is flowing from high energy level to the lower energy level, while transferring the heat from higher energy to lower energy, some amount of heat may be disordered or may be dissipated or may be leakages. Okay, and that leakages or disorder is nothing but entropy, which is tells us about entropy by the second law of thermodynamics. Okay, and the third law of thermodynamics is nothing but the entropy approaches zero at absolute zero temperature, means the temperature at which we can't actually, it is not possible to achieve zero absolute temperature, but some of the scientists are in a phase to achieve it. But at absolute zero temperature, the entropy or the disorder of the system is zero. That is what it tells us about third law. Okay. So right now we have just seen that what is the thermodynamics. First of all, it is the internal energy property of that system which tells us about thermodynamics. In thermodynamics, we are dealing with heat, work and properties of that system. Okay, and for analysis of any thermodynamic system, we are considering, or we are only in a search of equilibrium states. Okay, so what is the heat transfer? In first lecture I have just elaborated you. So heat transfer is nothing but the property or the energy that only caused due to the temperature difference. Okay, so the heat transfer is an energy movement, okay, or the property or the energy movement due to the temperature difference. If there is a no temperature difference, then there will be no heat transfer takes place. Okay, so it occurs in a non-equilibrium condition. Same the implications like in first line. Okay, if there is a temperature difference, then there is a non-equilibrium state, and if there is a non-equilibrium state, then only the heat transfer takes place. Okay, it is a simple thing. So there are three modes of heat transfer: conduction in solids, and convection in fluids, and radiation due to the electromagnetic waves. Okay, so these are the three types of heat transfer which takes place in everyday life, but we are going to see these heat transfer types in each separately in further lecture. But right now just you understand that the conduction is a type of the heat transfer due to the solids, or is generally present in solids. Convection is a type of heat transfer. It generally we can see in fluids. Fluids means gases or liquids, and radiation is a heat transfer due to the electromagnetic waves. Okay, so as our lecture states, what is the difference between the thermodynamics and the heat transfer? So basically the thermodynamics here, in thermodynamics we are encountered, or we focus on the energy amount and equilibrium state, rather than in heat transfer we just focusing at the rate and the transfer mechanism. Okay, we are not here in heat transfer, we are not taking it in equilibrium state. In a heat transfer there is always a non-equilibrium state, because when there is a temperature difference, then only the possibility of heat transfer is going to be takes place. Okay, so time in a heat thermodynamics is not considered, because we are dealing with the end points, okay, of any processes, and as compared to heat transfer, in heat transfer the time is critical, because as the time passes, okay, as the time passes, what is the change in a temperature difference along the length or along the width or along any distance is to be calculated. Okay, the scope of the thermodynamics is broad, which includes work, heat, also the system properties, but the heat transfer, the scope is only specified to the heat. How the heat is transferred takes place, only we are dealing on that point. Okay, processes, as likewise I said in earlier processes, the thermodynamic process is must to be in equilibrium state, and in heat transfer the process must be in non-equilibrium state, then only heat transfer occurs. Okay, the use of the thermodynamics is for analysis. Okay, analysis of any system, how the system at the start and at the end will going to perform, or will going to deliver some work or heat or whatever the change in the system properties, we are going to analyze the things in the thermodynamics. And in heat transfer our focus is only up to design. Why? Because we are known that the heat transfer is only taken place due to the temperature difference, and that temperature difference we have to maintain according to our condition. Okay, so for our condition we are designing the heat transfer, whatever may be the problem or whatever may be the statement. Okay, so mathematical foundation in thermodynamic, likewise I said in a first slide. Okay, the internal energy plays an important role. How the internal energy is changing according to the state points, like let's say starting point or end point. Okay, in thermodynamics, in first law, as the first law says that energy can't be created or nor be destroyed. It can be converted from one form to the another form, and that form without with the conversion will have certain internal energy change. Okay, so internal energy change is delta U. Okay, m is a mass of that system, cv is a specific heat at constant volume, and delta T is a temperature difference of that system and the surrounding. Okay, this equation is applicable for constant volume process. Let's say take an example of a beaker completely closed, and in that beaker let's say you will have water vapors trapped in that beaker. Okay, that is the example of controlled volume. The volume of the water vapor in that beaker is going to be constant. Okay, the volume of that water vapor is not going to change. Okay, but in engineering there are some systems like constant pressure system which are used for or which are referred as flow processes. Okay, so same in that beaker, if you put inlet and outlet valves, okay, or inlet and outlet ports, then that system with the inlet and outlet ports of a beaker will have a constant pressure process. Okay, and for that constant pressure process, the change in internal energy is nothing but mCp delta T, where Cp stands for specific heat at constant pressure. Okay, so in thermodynamics we are dealing this mathematical foundation for internal energy change, and in heat transfer, for as we see in this previous slides, for heat transfer in a conduction we are going to see a Fourier law. Okay, and in convection a Nusselt number correlation we are going to see in this in further lecture. Of this lecture, thermodynamics versus heat transfer is nothing but thermodynamics plays, or thermodynamics is going to see how much energy is going to transfer. Okay, and the heat transfer is going to say how fast with respect to time. Okay, how fast is going to how fast the energy is going to transfer. Okay, at last thermodynamics is nothing but how much energy is going to transfer, and the heat transfer is nothing but how fast the energy is going to be transferred. Okay, with respect to time. So practical applications of these, the thermodynamics is used to analyze the energy balances in system like refrigeration cycle, IC engine cycle, or any gas turbine cycle. Okay, and heat transfer is used to efficiency to analyze the efficiency in design. Means what? According to our comfort or according to the need, the temperature difference is going to be set, and according to that the system is going to be designed, and how the efficient system is going to be designed is decided with the use of heat transfer in heat exchanger or in condenser. Okay, so when numerical is there. Okay, so a 1 kg of a liquid water is initially at 20 degrees Celsius is to be heated to 100 degrees Celsius in a teapot, and the teapot is equipped with 1000 watt of electrical heating element inside it. Okay, so a teapot is 0.5 kg in mass and has an average specific heat of 0.7 kg per kilojoule degree Celsius. Taking the specific heat of water is 4.18 kilojoule per kg degree Celsius, and disregarding any heat loss from the teapot, determine how long it will take place for water to be heated. In this question, I will draw here. In this question, a teapot. Okay, let's consider this square as a teapot. Okay, this teapot having a water, okay, initially at 20 degrees Celsius, and we want this water to be heated at 100 degrees Celsius. Okay, so for heating this water, electrical element, let's say you in your hostel you are using the electrical rod for heating your bath water. Okay, so similarly here we are using electrical heating element of 1000 watt to heat this water from 20 degrees Celsius to 100 degrees Celsius. Okay, and here the specific heat of this teapot and the water are given, and here specifically mentioned disregarding any heat loss from the teapot. So the energy loss from this teapot will be neglected. Okay, so in total the energy in minus energy out is equal to total internal energy change. Okay, so total internal energy change of this system consists of water and teapot. Okay, the water is having some specific heat and the teapot also having some specific heat. We are just neglecting the heat losses from the teapot. Okay, so we are assuming the heat loss from this teapot as a negligible as said in example. So E out, that is energy which is going out from the system, we are taking as 0. So energy in that system is equal to delta U, means change in internal energy of a water plus change in internal energy of teapot. Likewise, in before I just put that numerical or mathematical equation for change in internal energy is equal to mCp delta T. Here mCp delta T represents this system is at a constant pressure system. Okay, so mCp delta T of water is internal energy change of water due to the temperature difference from 20 to 100 degrees Celsius. Okay, similarly for teapot, the change in internal energy for the temperature difference from 20 to 100 degrees Celsius. Just put these numerical values in this equation. So we got E in as for water is having mass 1 kg. Its Cp, that is specific heat at constant pressure, is given as 4.18 kilojoule per kg degree Celsius, and change in a difference, that is delta T, is from 100 to 20 degrees Celsius. So in this total E in, that is energy in, is equal to the internal energy change of water and internal energy change of teapot. So water having mass of 1 kg stated here, and water having specific heat of 4.18 kilojoule per kg degree Celsius. Okay, and the temperature difference is of 100 minus 20 degrees Celsius. Similarly, we can put numerical values for a teapot of 0.5 kg, teapot of 0.5 kg, and its specific heat is 0.7 kilojoule per kg degree Celsius, and the temperature difference of 100 to 20 degrees Celsius. If we calculate using the engineering calculator, then total energy inlet is 362.4 kilojoule. So we are here to calculate how much time it will take to convert this 20 degrees Celsius water to 100 degrees Celsius. Okay, so total energy here, inlet internal energy, is 362.4 kilojoule, and for converting this energy we are using 1000 watt electrical heating element. Okay, and for this the total time is the total energy transfer divided by rate of energy transfer. So total energy, how much total energy is going to transfer, we have just calculated, that is 362.4 kilojoule, and this 1 kilojoule per second is nothing but 1 kilowatt or 1000 watt of electrical 1000 watt or 1 kilowatt, which is nothing but 1 kilojoule per second electrical heating element is going to be used. So dividing this, we will get 362 seconds is approximately nothing but 6 minutes. So in this numerical, we just see that for heating the 1 kg of liquid water initially from 20 degrees Celsius to 100 degrees Celsius, we need 6 minutes with the use of 1000 watt electrical heating element. So in this lecture we have seen that the difference between the heat transfer, okay, and the thermodynamics, and these are nothing but complementary with each other, okay. So heat transfer is nothing but how fast or how slow the heat transfer takes place, and thermodynamics is deals with how much energy or how much quantity of energy is going to be transferred, okay. And both are essential for system design and analysis. So we have seen the laws for the thermodynamics, and we have in previous lecture also we have seen the how the heat transfer is going to plays an important role with the difference of temperature. If there is a no difference in temperature, then heat transfer can't occur. So we have seen that. So thank you very much.